examples for Bussgang theorem. First example is a hard limiter. For a hard limiter, we have this function. This is a hard limiter. The function this is input, and g of x is equal to +1 for x positive and -1 and so on. So you could see easily that this is equal to twice a unit step function and then -1. So in this example, dy over dx is equal to twice the derivative of unit step function is delta x. Okay, so in this case, if I want to calculate k is equal to expected value of twice delta of x of t. How can I calculate that? So obviously expected value of everything is equal to the value it can take, this is the value, times its PDF. So delta x multiplied by any function is going to be, because you have delta of x minus x naught times any function, any like g of, let's say, x is always equal to g of x naught. Now in this example you could say x minus 0, so this guy is equal to twice delta of x of 0. Now 2 and fx of 0 are constant, they come outside of the integral, gives you this one, and then you have integral of delta of x dx from minus infinity to plus infinity, and the area under delta function is equal to 1, so this simplifies to be equal to 1, and then your answer becomes 2 fx of 0. So this is my final answer. So and obviously fx of x is equal, because I have a Gaussian distribution, is e to the power of minus x minus mu minus expected value of your random variable, which is minus 0, to the power of 2 twice the variance, twice r x of 0, divided by a square root of twice pi, and the variance is equal to r x of 0. Now if I replace this x by 0 here, if I put this 0 here, I have to put e to the power of minus 0 to the power of 2 twice r x of 0 divided by a square root of 2 pi r x of 0. Okay, so I get 1 divided by square root of 2 pi r x of 0. Now I have to put this one multiplied by 2 here, so so I get twice k is equal to twice fx of 0, which is equal twice times 1 over square root of 2 pi r x of 0, which if you simplify these 2 and these 2 will be simplified to this final answer. The second example I would like to have is a neuron. A neuron can be approximated like a function like that, a tangent inverse of, let's say, tan inverse of x. So for x infinity becomes pi over 2, and for x equal minus infinity, so you have to asymptotic one, because tangent of pi over 2 is equal to infinity, and tangent of minus pi over 2 is equal to minus infinity, so their inverse is like that. So it's a symmetrical function around 0, so it's kind of like x. So for this function, which if you try to plot it, you will get a curve like that. So here d2, the derivative of your function, d2 dx of g of x is equal to the derivative of tangent inverse is equal to 1 divided by 1 plus x2. So k will become equal to expected value of this function g of x, which is equal to expected value of 1 divided 1 plus x2, and then this is equal to integral from minus infinity to plus infinity of 1 over 1 plus x2, and then you have e to the power minus x2 divided by 2 or xx of 0 divided by square root of 2 pi r xx of 0 and then dx. You have to calculate this integral to calculate for this. So there are in neural networks this Bussgang theorem is very useful because regardless of the shape of this one, you will get a constant, and this constant represents just an integral. So you can calculate this one in order to calculate.